Hey guys, welcome back. In this session, we're going to be going through a design challenge, or one of the design challenges that we have on our membership program. So this is a live session that we had this week where we're talking through all of the student projects and all of the design challenges that they're working on. So I'm going to put the design challenge up on screen now, so you can pause the video and then you can have a go yourself to see if you can complete the challenge, and then you can watch the rest of the video to see how I did it, or see how we did it. I'd suggest reading the design challenge very carefully and reading through all the steps, because this will lead you to the understanding about how to go about this quite efficiently. So yes, read it very carefully and this will give you all the hints that you need. So this is just a small challenge, so I wouldn't spend much more than maybe a half an hour to an hour working on this. The idea of this script is really to just show the principles of parametric and computational design, which is driving geometry through numbers. So in this case, our number system, or our numerical basis, is the relationship between our attractor point and our grid of points. We are then using this to drive a geometrical change. And this is the basis of computational and parametric design. So while this seems like a very simple design exercise or design challenge, it encompasses a lot of the foundational ideas of what we do as computational designers. So just keep that in mind as you're working through this. Number systems and very basic elements drive geometrical change. So good luck with the design challenge. Have a go now and then watch the rest of the video afterwards. And if you have any comments, please put them below. I'm going to give a quick overview of this intermediate design challenge that just while you're getting ready. And the idea of this design challenge is to have a series of disks that are all pointing towards and facing a attractor point. It's kind of an extension of what the attractor is, but instead of having using the attractor to affect the height of something, we're now using it to affect the direction of something. So using a center point of a hexagonal grid, so I'm just using a hexagon grid, create disks that are perpendicular to an attractor point. And I've put the components I've really listed out exactly, if you read this very carefully, exactly how this kind of works. But on its most basic level, what we are doing is we are creating I use this multi-directional slider to create a point. So this is all we have. All I have is a point. We could use here a XYZ point. That is also perfectly fine solution. We would have sliders which are defining the X direction, the Y direction, and the Z direction. So these two things, this section here, the attractor point here and the attractor point here, are exactly the same. I have control of my Z height, my X, and my Y. The only difference is that with this top one, I'm setting the X and Y with this multi-directional slider, it's a cool interface, but I can't really, I can set the upper and lower boundary of it, but I can't set a specific number. So say I wanted my X coordinate at exactly 10,000. I can't do that with the multi-directional slider. I can only get it kind of approximately. So that's just one thing to keep in mind. But it's a nice little user interface where we can move this point around. So we have an attractor point, which is just set in Grasshopper. The other thing that I said I was going to do is it was going to use a hexagon grid. So I have my attractor point here, which you can see moving around, and it's approximately moving around over the top of the hexagon grid. The hexagon grid actually outputs, and it has, if I put a point value into this, actually outputs the center point, but it doesn't it doesn't preview them. It's the only annoying thing. So this p value here are the center points of all of the hexagons. So it's just a center point. All we're doing is drawing a line from the center point of our hexagons to our attractor point. And what this is doing is it's giving us, and this is all live linked, And it's giving us a direction. It's giving us a vector. The start of the vector is the center of the hexagon. The end of the vector is our attractor point. And because, every single one of them is different because of the angle, and, so every single one is a different length, it's a different distance, but it's also a different angle. And the idea, and I noted in the design challenge to use circle CNR, and one of the tricks of components like this is to be very mindful and very clear. They shouldn't be as daunting as they look, because and if we look in the C and curves, and we have our primitive, we have all of our circles here. So circles, there's many different ways to create a circle, and that's the same in Rhino as well. If you look in the circle component, we can go from the center, we can go from I don't know, two points, two edges. We can go from 3 points could define a circle. There's many different, they're all a circle in the end, but there was a different process of creating them, which is probably quite representative of most things that we do in Grasshopper. There's many different ways to do the same thing. And so, yeah, the circle CNR is quite good because what it does is it gives us a center point. And if we read through the inputs of this component, we know that, okay, the center point is going to be our hexagons. I already know where I want my circle to be drawn. So we can answer that question here. And the center point of the circle is this. The normal is a different way of saying the direction, or the perpendicular vector. So all we're going to use to do that is our line. This is going to be now interpreted as a direction, as a vector. And we're also, we have a radius. So all of them have the same radius, which is defined by this slider value. And so you can see we have circles that are all perfectly aligned and facing our attractor point, which we can move around like this. In the top view, this is, the relationship is, you can kind of create some cool pieces of art like this, I would imagine, or I don't know, you could turn this into a facade pattern, or I don't know, whatever it is. It's just the principle of using, this. I mean, technically here the number system is this is the direction, the vector here, and using that to define these. The only other thing that I put in the design challenge is, what does adjusting the Z height of the attractor point have? So if you can imagine our point and all of our points and our grid are, when they're perfectly the same plane, our lines are going to be perfectly flat on plane. So when we do a perpendicular curve, a circle, they're all going to be perfectly vertical. So you can see this if I go to the top view, they're all perfectly vertical because the grid point and the attractor point are in the same plane. If we raise this and we increase the height of the attractor point, well, this is because this is doing the exact same thing, but it's actually working in 3 dimensions now. You can see my grid on the bottom. My attractor point is higher than the grid. So all of my circles align to it. And we get, and they're actually following my attractor point in 3 dimensions. So this thing is, it's working in 2 dimensions, 3 dimensions. It doesn't, it doesn't really matter at all. And you could imagine this could be, the algorithm to track solar panels against the sun being the attractor point, and these panels being the solar panels. But yeah, that is, it's a very, very simple set of components. But the idea of this little intermediate design challenge is, well, just to work through those kind of ideas, that we can use the direction of an attractor, to actually adjust our geometry.
There's one tip here, plus points. So I'm not going to go through this, so you can actually do this yourself if you want, but can you also control the radius of each circle based on the distance to the attractor point? So could you, how do you change the size of the circle based on the distance to the point as well?
So I hope you found this design challenge useful and that you learned something and also got some cool images from this. Like I said, it's a very simple script, but it encompasses a lot of the foundations of computational parametric design, i.e. driving geometrical change with numbers. I can't say this enough, and I say it all the time. You're probably getting bored of this, but this is the foundation. And if we start from this, everything that happens afterwards is going to be much more efficient and far easier to control, regardless of whether we're creating a piece of artwork, like in this situation, or a facade of a building, or much more complex things. We start from very base principles of numerical relationship and use that to drive geometrical change. Once you start getting your head around this foundation, then Grasshopper starts becoming far, far easier. So our members on our Computational Mindset membership are running through design challenges like this every week and building up that foundational knowledge. So if you're interested to join, all the information is below, and I look forward to having you on our membership. That's it for now. Thanks for watching, guys, and let me know if you have any comments in the comments below. I'd love to hear what you think about this. Thank you very much, and I'll see you next time.